Hey everyone, this is a Algebra 1 review lesson that will have some new aspects to it that you likely probably didn't see in Algebra 1 because they're very IB. So some new vocab and new words, so I would really encourage you to, I would hope that this happens typically when you're doing video lessons, that you have your notes out or you have this PowerPoint printed or some things that you're able to work through problems with me and sometimes even before me, right? And add some things to your notes. So what we will be doing, and maybe you already had a chance to read this, is using our knowledge of algebraic operations and what we know about linear functions, we're going to successfully solve and describe a system of two linear equations. So a system is I have a set, and when I'm saying solve, my goal is to find the point of intersection of those two lines, right? We're going to be doing this algebraically. You may have some familiarity with doing this graphically, and that's great. And it is good to picture that in your mind to support the algebraic understanding, but we do want to have an understanding of how do you solve this algebraically and what are the different ways you can solve it algebraically. You might be familiar with substitution, right? If I have two equations, I can solve one for a variable and plug one into the other. Right, so that might be something you're familiar with, and we're going to talk about that as well as another one. This idea of describing a system, it's basically saying how many solutions does my system have, right? And so that will be a little new or additional throughout this lesson. So solving a linear system, lines, right? We're working with lines here. A system means that you have more than one at the same time, right? Like they're a system. So our goal is to find the point where the two lines intersect, as I just said. And it's if any, right? Like you can have two lines that are, what are those called when they never intersect? Is it parallel? Right? Or to find a point that makes both equations true at the same time. There's three different ways we could achieve this goal. Graphically, by hand, or with a calculator, right? We really haven't used calculators. Usually an estimate. The add down method, it really, it could potentially work under any situation, but like there are times where this is better than others. And this is one of those things that's like, you got to practice, right? And so I know which one to use when. I can look at something and say, this is going to be better, but that takes practice and that takes time, right? And so you can't really hold yourself to a standard of, I'm going to right now, by the end of watching this video, I'm going to know when I need to use add down and when I need to use graphically, or when I need to use, what's our next one? Substitution, right? Like I don't want you to think right now that you're going to walk away and know that. Like this takes time and this takes practice, and that's why practice is so important. Add down method is really more formally known as linear combinations, right? And then finally we have substitution. Whoa. Which always works, right? You can always solve and plug in. Sometimes it's not as pretty as others, but you can always do it. So simultaneous linear systems. For now, we're only dealing with a system of two linear equations. This is where we're going to review. When we come back together, you will be looking at a system of three. And that will actually lead nicely into our next unit, which you got a little bit of time before that, but it does lead nicely into that. So your solutions, two lines will intersect. Oh, check this out. You've got a solution that's a point. Like, you really want to emphasize this. Your solution is a point. It is a coordinate point. Right? You could have two lines that we talked about this for parallel. Your solution is the empty set. There is no solution, right? That's what this here indicates. There is no solution. Your two lines could be coinciding, meaning they lay on top of each other. That means that your solution is an equation because there is an infinite number of solutions. So think about how I'm going to represent my answers. I might represent it as a point. I might represent it as the empty set. I might represent it as an equation. I'm not just going to represent it as two different numbers, right? I'm not just going to represent it as saying the lines are coinciding. Oh, sorry. This is the piece that I would certainly, if you're writing nothing else down, that this goes on your paper. So IB uses these terms, and it's not, this is not, you would be able to find this if you went to go look it up. Like if you Googled what does independent consistent mean, it's going to tell you, right? Like it's not, I'm not like making it up. So independent consistent, that is what IB is referring to as a point as an answer, right? That you have one solution, that system was independent consistent. If you have it where there are no solutions, that is what we refer to as an inconsistent system. If you have it where there are an infinite number of solutions and you're writing the equation of a line, that is what we call dependent consistent. Independent consistent is one solution. Inconsistent is no solution. Dependent consistent is infinite solutions. These are terms you need to know. And these are terms that will come up often, right? And we're going to be working with them. So I would definitely make sure that this makes it somewhere onto your paper. So this is what, and on the, you guys have textbook homework. This is on the homework, even though it doesn't say it in the textbook, it says it on the directions for the homework on our weekly page that you should be describing the solution. This is what I mean. This is what is indicated there. These words should be on your homework, and you should be in the habit of telling us what type of system it is. Okay, so this should happen on your homework. Right, so this means there's one unique solution. There's no solution, there are infinite solutions. Let's go through an example. And so just like I did on the homework where I told you which problems, I think it's 6 problems if I'm remembering correctly. 3 of them I said substitution, 3 of them I said linear combinations. I assigned some odd problems. Odds are in the back of the book. Go and check them. That's the purpose. That is why I'm assigning odds also. I would also expect that your work is being shown so that we can provide you feedback and we can see what needs work. So I'm going to use substitution to solve. So this means that I'm going to want to solve for one of the variables and then plug in. So I'm going to solve for x, right? X equals 8y plus 6. And then I'm going to take that and I am going to substitute that in right here. So that will give me 5 times 8y plus 6 plus 8y equals 0. Right? And now I've got one variable. Let me go ahead and distribute 40y plus 30 plus 8y equals 0. 48y. Is my math right? Yeah, right? I'm fine. Am I fine? I think so. I think I'm good. Right? 8 times 5 is 40. 48y equals negative 30. Divide by 48. Divide by 48. I should probably simplify that. I get negative 15 over 24, which simplifies more, right? They both divide by 3. Oh, because these both divided by 6, didn't they? Negative 5 over 8. That's my y value. So here, I'm gonna start to write my solution. It's gonna be a point. Okay, then I'm gonna go ahead and I have to take that and plug it back in. I'm just gonna plug it back in this one where I already solved for x. Right, so I've got 8 times negative 5/8 plus 6. That's nice. 8 times negative 5/8 is just gonna be negative 5 plus 6 gives you 1. So my solution is 1, negative 5/8. So what type of system is this? Independent, consistent system, right? Get yourself in the habit of doing that. What would the graphs look like? They would intersect at one point. Oh my goodness, right? They're going to intersect at one point, and this is where they're going to intersect, right? This is what makes both of them true. If I plug in a 1 and a negative 5/8, a 1 and a negative 5/8, it makes both of these true. That is where the two intersect. That is the point that they share. Let's do another one. So for this one, I'm saying use linear combinations to solve. Sorry, I got to give you the one to do there. Oh, darn. It went away. What did I do there? Linear combinations. It's a good thing I'm here to add this in. So this is going to be the add down method, right? So I need a variable to cancel. What I can do, and we talked a bit about this when we did standard form, is I can dilate, right? Like I can multiply through by anything as long as I do it to both sides of my equation. So I can pick anything to multiply by. I'm going to choose to multiply this second one by 4. I'll go with 4, right? So I now have my first one, it's 8x minus 4y equals 12. I hope you know why I picked 4. Negative 8x plus 4y equals negative 12. I go to add this down. 8x minus 8x, right? I'm adding. Oh my God, that cancels. Negative 4y plus 4y. Oh my God, that cancels. 12 plus negative 12. Oh my God, that canceled. So I end up with 0 equals 0. Oh my gosh, that got rid of both of my equations. But this is true, right? So what does that mean? Well, that means that these are coinciding lines. They are the same line, right? That means that this is a dependent, consistent equation. I'm sorry, system. I was thinking ahead to what I was going to say next. So that means that my solution needs to be an equation. It is the equation of the line. Both these are equations of lines, right? Maybe I want to just write one of them. I don't care. Negative 2x plus y equals negative 3. Maybe you want to write it as y equals mx plus b, and you're going to write y equals 2x minus 3. I don't care, but your answer is an equation, and it is the equation of the line because it is the line, right? So what happened here is I went to go do linear combinations, right? I went to go multiply through by a number so that when I added down, one of my variables canceled. That's what linear combinations does. When I did that, everything canceled. But I got a valid statement here, right? Like everything canceled. That means that it is dependent consistent. That means that these are the same line. One is just a dilation of the other. If I went to go solve them both, I would end up with y equals 2x minus 3 down here. And oh my goodness, if I add 4y, I'm sorry, why would I do that? If I subtract 8x and then divide by divide by negative 4, I'm still going to get y equals 2x minus 3. That is the equation of my line. Pretty neat. Let's do substitution here. You know, if you haven't thought about stopping the video to try any, this might be a really solid time to do so. I'm just going to take the first one, and I'm going to solve for x. 2x equals 3y plus 7. I'll go ahead and divide by 2. I don't care if you see what's going to happen. I still want you to do this by substitution because that's what the directions say, and we should get used to how we have to show this process. I'm going to take this and plug it in for x. So 2 times 3 halves y plus 7 halves minus 3y equals negative 4. When I distribute, this works out nice. I get 3y plus 7 minus 3y equals negative 4. 3y minus 3y, those go away, and I get 7 equals negative 4. Well, that certainly is not true, right? We actually know that that's false. Like, that is very false. So this here, when I get something like this means that the system is inconsistent, right? I get parallel lines. These are lines that would have the same slope but a different y-intercept. And maybe you see that because these are both in standard form and you're used to saying that, well, my slope is negative a over b. And they have the same slope, but my constant is different. Right? Very interesting. So here, my solution is just the empty set. There is no solution. So what we just did in this lesson, I didn't get too far into it, was, and I think really the biggest like new piece of this was naming the system and describing the system. So what you guys, your task is you have 6 textbook problems, right? Now that you have it, that you are going to be uploading to us. The expectation is that you are showing work. It indicates to you on the Canvas page, right? So where you access this video, if we are asking that you use linear combinations or we are asking that you use substitution, right? I'm not asking which one do you think is easier. It is extremely important that you practice both of them, right? So I gave 3 where you're doing substitution, 3 where you're using linear combinations. If you see an odd problem, check your answer in the back, right? So I want it showing works. Sorry, that was silly. The other piece that the textbook does not ask, but I am asking and that we expect that you are doing, is that you are describing the system. Get yourself in the habit and practice using those IB terms so that you are not waiting till later to grasp that concept, right? Like practice it as you're working. So when you've done those 6 problems, you are scanning it, taking a picture of it, screen, like however you're doing it, and uploading your work for us to see and review. So if you need to go back and look at anything, go for it. Otherwise, we will see you next time in class.